Hello, welcome back. We are on chapter 12 of Materials Kinetics, which is diffusion in polymers and glasses. Over the past several chapters, we've been dealing with diffusion in single crystals, crystals with defects, polycrystalline materials, as well as morphological evolution in polycrystalline materials. And today we're going to shift focus a little bit and turn our attention to non-crystalline polymers and glassy materials. So the outline for today is that we're going to briefly introduce non-crystalline materials. We're going to cover two different approaches to diffusion in polymers. One that is based on the Stokes-Einstein relation and what's known as the freely jointed chain model, and the second, which is based on the notion of reptation. From there, we're going to switch over to glasses, and this is going to be a more application-focused lecture with respect to diffusion in glasses, where we're going to deal with the ion exchange process, which is the process by which chemically strengthened glass is made. And we're also going to cover ion exchanged waveguides and anti-microbial glass. So let's dive in here. One of the common themes in non-crystalline versus crystalline structures is that oftentimes the basic unit is the same in both cases, where you can see comparing the glass on the left and the crystal on the right. The basic building block is the same, but the way in which they're connected is different. On the right-hand side with the crystal, these units are all connected in an orderly fashion. They're making these six-membered rings that get repeated. Whereas on the glassy side here, there's a greater variation in bond angles. There's greater variation in ring sizes and connectivity. And so even though it's the same basic unit, the fact that there's more randomness in how those units are connected leads to this non-crystalline glassy structure on the left compared to the perfect crystal here shown on the right. Now, the first method that we're going to use to study diffusion in non-crystalline media is the Stokes-Einstein relation. The Stokes-Einstein relation connects the diffusivity to some size A of a spherical diffusing particle within a viscous medium that has a shear viscosity eta. So the physical picture is that we're treating this particle, whether it's an atom or a molecule, as a sphere with an effective radius of A, and it is traveling in some medium, and that medium has a shear viscosity of eta. Now, this particle with radius A is traveling at a velocity of v, and then there is a drag force that is acting on the particle to slow down its velocity. That drag force is F sub d, and that drag force is directly proportional to the shear viscosity of the medium that it's in. So if you've got a more viscous medium, that means there's a greater drag force acting on that particle. Also, if the particle is larger, the drag force increases linearly with the radius of the particle and also linearly with the velocity of the particle. So the drag force is 6 pi eta times A times V. This is Stokes' law for the drag force that's acting on a spherical particle in a viscous medium. In order to get the Stokes-Einstein relation, we combine Stokes' law with the Einstein relation, which relates the diffusion coefficient d to the mobility of the particle, which is the velocity per force. So it is the velocity of the particle divided by this drag force times Boltzmann's constant times the temperature, and that gives us the diffusion coefficient. Now, putting these two together, if we take this equation here for the drag force, stick it into the denominator of the Einstein relation, that gives us the Stokes-Einstein relation. And you can see that the velocities have canceled out from the numerator and the denominator. And what we're left with is that the diffusion coefficient, d, is equal to Boltzmann's constant times temperature divided by 6 pi times the shear viscosity times the size of the particle. In other words, there is an inverse relationship between the diffusivity of the particle and the shear viscosity of the medium in which it's traveling. So the Stokes-Einstein relation is um, a law that works well if you have a spherically shaped particle in a medium, and the primary drag against that particle moving is in fact the viscosity of that medium. Where this breaks down is if you get to such a high viscosity that you're getting close to the glass transition range, or if you've got some complicated interconnected network or structure of this matrix such that it's not really acting like a homogeneous fluid, as what's being assumed here. So when we consider diffusion in polymers, of course, as you know, polymers are composed of molecular chains arranged in different configurations. The simplest of these would be polyethylene, shown here, which is just the CH2 groups linked together in a long chain, as shown here. And diffusion of these chains can follow two different types of situations. One is if you have isolated chains in a solvent of much smaller molecules. If that is the case, then the diffusion can follow fairly accurately the Stokes-Einstein relation. However, if you have a situation where you've got very long entangled chains, or chains that are interconnected with each other, the Stokes-Einstein relation may break down under those circumstances, and in that case, the diffusion in polymers is described by something called reptation. So we're going to cover both of these phenomena in this lecture. First, starting with the Stokes-Einstein relation, one of the problems is that is assuming a sphere, and a polymer, of course, is not a sphere. And so we need to make an approximation to say, what is the effective radius of a polymer chain if we're going to use that within the context of the Stokes-Einstein model. And the simplest way to do that is with this freely jointed chain model. This is a simple model in which the direction of each bond between monomers is assumed to be random and each monomer has a length here of little b. So if you start at one end of the polymer here at the origin, and each segment has a length of little b, and if you've got random angles between the segments of the polymers that are connected together, then this overall displacement from the beginning end of the polymer to the opposite end of the polymer after n segments, this displacement vector is given by capital R. And the mean squared displacement then is simply the number of units times the segment length squared, assuming that the angles are random. And so this then, if we take the square root of this is an effective radius that can be used in the Stokes-Einstein relation. So in this case, we're assuming that the solvent that this polymer chain is in is acting like a homogeneous fluid with a shear viscosity of eta. We've got an effective radius here of r, and then applying the Stokes-Einstein directly using this equation for this mean squared displacement, what we get is that the diffusion coefficient is equal to Boltzmann's constant times temperature divided by 6 pi times the shear viscosity of the median. And then the square root of this to give us the effective R is the square root of n. So that's the square root of the number of monomers in your polymer chain times b, the length of each monomer. And what this tells you then is that there is an inverse relationship between the diffusion coefficient and the viscosity, but also an inverse relationship between the diffusion coefficient and the square root of the length of the polymer. So as the polymer is getting longer and longer, its diffusion coefficient is going down. Now, what happens if you've got a really long kind of entangled web of different polymer chains? In this case, the process of diffusion is governed by something called reptation. This is a process that was proposed by Pierre de Gennes, Nobel Prize winner, to describe the motion of polymer chains in a densely packed and highly entangled system. The name here, reptation, is derived from the word reptile, and it's supposed to relate back to the snake-like motion that this is undergoing. Where basically, if you've got a particular polymer chain here, the assumption is that the motion of this chain is along the same axis that the polymer chain is occupying. So the movement of the chain is in the direction tangential to itself. And this snake-like motion is what gave rise to the name reptation. So here, the assumption is that there is a freely jointed head at the leading end of the chain, and this freely jointed head can find some other position in which to move to. So it can find some optimum region, for example, of lower density in which to advance. And as the head advances, it is pulling the entire chain behind it, and that chain is moving along the axis of the polymer chain that is occupying anyway. So the remainder of this chain is then following by an appropriate sliding motion. The chain can move equally well in the reverse direction as well, since the head and the tail are interchangeable. So basically, one end of the polymer chain is going to take a step forward, and then it pulls the rest of the chain behind it, and it follows this space that is already being occupied by the polymer chain. Now, if we assume that each polymer occupies some tube of length L through which the sliding motion occurs, and the tube mobility here, this mu sub tube is our tube mobility. That is equal to the velocity per unit force. So the velocity of the chain when it is pulled by a force F, that's what gives us the mobility. Then according to the Einstein relation, the diffusivity of the tube is equal to Boltzmann's constant times the temperature times the mobility of the tube. And then putting this together, if we are in one dimension, because the polymer chain is moving along the one dimension, the linear dimension of the chain itself, then the mean squared displacement is equal to 2 times the diffusion coefficient times time. The 2 is coming since it is a one-dimensional motion, and then this is equal to 2 times Boltzmann's constant times the temperature times the mobility of the tube times time. And so this is relating then the diffusivity of the polymer chain following this pathway through reptation back to its mobility and its mean squared displacement. Now, one of the important properties in polymer physics is what's called the reptation time. The reptation time is the time for a chain to fully displace the length of its original tube. And that reptation time can be denoted as little t sub L, where L is the total length of the tube. And using this equation here and solving for time, the time that it would take to for the chain to displace this full distance here, L. So if you put L in for R and solve for the time, we get L squared. So this would be the length of the chain squared divided by 2 times Boltzmann's constant times the temperature times the tube mobility. So in other words, the reptation time is increasing with the squared power of the length of the tube. And this reptation time is important because it relates back to the relaxation time of the polymer, the overall kinetics exhibited by the polymer system. So moving now into inorganic glasses. Inorganic glasses are very important for a wide range of different technologies. If you look at your smartphone, for example, there are actually multiple layers of glasses that are included as part of your smartphone. There is the outer cover, which is designed to be mechanically strong. It's chemically strengthened through the ion exchange process. Most likely this is, say, Corning Gorilla Glass. Underneath that is a touch sensor, and then there may be encapsulation glass to help protected from the outside atmosphere to prevent moisture and oxygen from reaching the electronics. Depending on the technology of the display, basically there's different types of glasses that can be included to act as a substrate material or a color filter or front plane for the high resolution display in your smartphone. You can think of the display itself as being like a sandwich where you've got two pieces of glass that are like the two pieces of bread in your sandwich. And then the thin film electronics that make up the pixels are in between those two slices of bread. So you've got two layers of glass with the electronics in the middle, and then another piece of glass on top that acts as the protective cover. In many smartphones, there's also another piece of glass on the back of the phone that provides protection off the back, and that also needs to be chemically strengthened in order to provide good mechanical resistance for the smartphone. So each one of these different layers of glass requires highly engineered glass product to meet all the requirements. For example, what we're going to focus on here is actually this outer cover. This is, for example, Corning Gorilla Glass. This is a chemically strengthened glass that uses an ion exchange process governed by diffusion in order to strengthen the glass and provide the mechanical protection that the smartphone needs against things like scratches, indentations, and drops. And so what I'm going to do in this next part of the lecture is walk through this ion exchange process by which chemically strengthened glass is made. So to make chemically strengthened glass, we start off with an as-made piece of glass that has some small alkali ions in it. Normally, this is sodium. It could also be lithium, but it's got a large concentration, probably about 15% or so of small alkali ions in there. So if we suppose that the glass starts off with sodium, then after this glass is made, this glass gets submerged in a molten salt bath, where that salt bath contains larger alkali ions, such as potassium. If you've got a glass that has lithium, you could also use a sodium-containing salt bath. But in this example, we've got a sodium-containing glass, so we need a molten salt, and typically this is potassium nitrate. So the cation here, it has the same charge as the cation in the glass. They're both a +1 charge, but the cation in the molten salt is larger than the cation within the glass. And now what we have is a concentration gradient between the salt bath and the glass. So you've got a high concentration of potassium in the salt bath and a high concentration of sodium in the glass. And they are going to want to undergo an interdiffusion process where the sodium hops out of the glass and into the salt bath and gets replaced by potassium ions from the salt bath. So before the ion exchange process, the glass is full of sodium and the molten salt bath has potassium. But as the ion exchange process proceeds, those sodium ions are going to hop out of the glass and become replaced by potassium ions from the molten salt. And this process occurs on the timescale of several hours and at temperatures on the order of 400 degrees C. You need to pick a temperature that is going to be well below the glass transition temperature of the glass to make sure that the glass is not relaxing on that timescale. But the temperature has to be high enough to ensure that the salt, in this case the potassium nitrate, is able to be in the molten state, and also to make sure that you've got fast enough diffusion kinetics to enable this ion exchange process to occur. And the way that this enables the glass to get strengthened is by incorporating a compressive stress at the surface of the glass. And the steps that are involved here are that when this potassium for sodium ion exchange process takes place, potassium has the same charge as sodium. So from a charge balance point of view, the glass is happy, but the structure of the glass was optimized during the melt quenching process around this smaller sodium ion. So when the larger potassium ion tries to take its place, it's kind of like taking out a tennis ball and stuffing in a bowling ball instead. It doesn't quite fit, and the glass wants to expand in order to accommodate this larger potassium ion. So the volume of the glass wants to increase as a result of this ion exchange process, and it wants to increase more in those regions where you have a higher concentration of potassium. In other words, nearer the surface or nearer this interface between the glass and the molten salt, that's where you have a higher concentration of potassium. So that's where the glass wants to increase in volume more. However, in the interior of the glass, it's still all sodium. And so even though this concentration profile of potassium wants to lead to a strain profile where the outer parts want to expand more, the inner part of the glass doesn't let it expand because it is still as formed with pure sodium. The potassium hasn't had enough time to penetrate all the way into the middle of the glass. And so as a result, this strain profile gets converted into a stress profile because the outer layers of the glass want to expand. They're not allowed to expand because they're bonded to the interior of the glass, and that strain profile gets converted into a stress profile. So the steps that are involved here are that you've got a concentration profile that develops as a result of the interdiffusion process. That leads to a desired strain profile that then gets converted into a stress profile. And since the outer surface of the glass wants to expand, but it's not allowed to expand, it actually gets pulled into compression. And there is this compressive stress layer that is developed at the surface of the glass that provides a barrier to fracture. That compressive stress is on the order of about a gigapascal. And so if you want to break a glass that has been chemically strengthened, you have to overcome not only the intrinsic strength of the glass itself, but also this additional compressive stress layer on the order of 1 gigapascal in stress. And so as a result, this ion exchanged chemically strengthened glass is a lot stronger compared to the as-formed glass prior to the ion exchange process. Now, recall from one of our earlier chapters, I believe this was chapter 3, that the most important question that we want to ask with an interdiffusion process is there a zero net flux? So if you've got an interdiffusion of two different types of atoms here, A and B, moving in opposite directions, the question is, if you add those fluxes together, is that net flux zero? And if it is zero, what that means is that these atoms are simply switching positions with each other. And in that case, instead of having separate diffusion coefficients for the two different types of atoms, instead of having separate dA and dB, we have just one independent diffusion coefficient, since the diffusivity of both types of particles are equal to each other. They're both moving at the same rate if all they're doing is merely swapping positions with each other. And that is indeed what we have as the case here with ion exchange glass, that in order to maintain charge balance, there needs to be a 1-for-1 exchange between sodium ions and potassium ions. And so we've got one effective interdiffusion coefficient that accounts for the swapping process between sodium and potassium. Now, the concentration profile that we get from the ion exchange process is a simple modification to one of the diffusion problems that we solved in chapter 4. And that problem was if we had a constant concentration of our diffusing species at the surface, and we assumed a semi-infinite medium, the solution to that problem, which we solved through Laplace transforms, was this complementary error function shown here. So it's the Earth C of the position here, x, divided by the square root of 4 dt. And that's what provided this complementary error function shape of the concentration profile as a function of distance going into the glass. And the assumption here is that this is a semi-infinite medium, so that this is going to decay basically, in this case, by the time we get to the halfway point or the midpoint of the glass. And since we have two surfaces of the glass, we've got another complementary error function term here, which is acting in the opposite direction. So it's acting in the minus x direction, and it's shifted by the distance, which is the thickness of the glass itself, L. And so we've got this additional complementary error function term where instead of the x in the numerator, it's the L minus x. And that's what gives us this symmetric concentration profile, which is the ion exchange from the other side of the glass. So the thickness of the glass runs across here from 0 to L. And from the left-hand side, the potassium ions are coming in. They've got a maximum concentration at the surface, and then they decay down to 0. And then from the other side, we've got a symmetric concentration profile, also following this complementary error function shape, with a maximum potassium concentration at the surface, decaying down until it gets to 0. And if you add this up, then this gives you the overall concentration profile of the potassium going into the glass. Then 1 minus that would give you the sodium concentration. Now, one thing that we have here is the scaling factor, which is the alkali oxide concentration in the glass, minus the base concentration of the invading alkali oxide. So in this plot, you see that this goes all the way down to 0. And that's because the assumption here on this plot is that there's no potassium initially in the glass itself, that this glass is just sodium oxide in terms of its alkali content, and then that sodium oxide gets replaced by potassium as it comes in. However, if you have some potassium oxide in the initial glass concentration, instead of decaying all the way down to 0, it would decay down to whatever the concentration of the potassium oxide is in that initial glass. In some of the earlier chemically strengthened glasses that were used, there was some small concentration of potassium oxide in the glass, but in later iterations of chemically strengthened glass products, generally that goes to 0. So in most cases, the C base here is 0, and we don't have to worry about it. Now, how do we generate the compressive stress in the ion exchanged glass? Once we have this concentration profile here, minus whatever the base concentration was in the initial glass, and this is often equal to 0, that concentration is going to lead to a strain in the glass. And the proportionality constant between the concentration of the invading species and the strain that the glass experiences is this parameter here, B, which is called the network dilation coefficient or linear network dilation coefficient, also known as the Cooper coefficient in honor of L. Cooper, who was one of the pioneers in developing the physics of the ion exchange process and chemically strengthened glasses. So this Cooper coefficient or network dilation coefficient B is the proportionality constant that relates how much the concentration of the invading alkali species is changing, and then how much strain that you get from that. This can be thought of as being analogous to a coefficient of thermal expansion, where a coefficient of thermal expansion tells you how much strain that you get per unit change in temperature. Instead of that, the Cooper coefficient tells you how much strain you get per unit change of concentration. So, for example, for every 1 mole% of ions exchanged, how much strain do you get as a result of that? And that is this Cooper coefficient. So a greater Cooper coefficient means a greater amount of linear strain. Now, the next step is to convert this linear strain into a stress profile. And if you have a planar geometry, the conversion from strain to stress is given by this factor that relates to the elastic moduli. That's minus the Young's modulus here, E, divided by 1 minus the Poisson's ratio. And that governs the conversion of strain to stress, where everything here would be the average amount of strain that you have, and then that gets converted to stress, and that gives you the stress profile here, sigma, which is a function of the position x into the glass and the time t. Now, one thing that you'll notice here with this concentration is that this is the concentration minus the average concentration, where this average concentration is simply whatever the average concentration is averaged through the thickness of the glass. So if you take this concentration and average it from 0 to L, so averaging across the thickness, that's what gives you the average concentration. And this subtraction of the average concentration is here because the stress profile needs to satisfy the force balance condition. That force balance condition says that if you integrate all of the stresses through the thickness of the glass, so integrating this over x from 0 to L, that integrated stress must be equal to 0. Or in other words, all the compressive stresses that we develop at the surfaces of the glass must be balanced by an equivalent amount of integrated tensile stresses in the interior of the glass. You can't just have compressive stresses at the surface without an equivalent balancing amount of tensile stress in the interior. And so this subtraction of the average concentration is what ensures that the force balance condition is met, so that if you integrate this entire expression from 0 to L, that it will be equal to 0. So what this means is that following this expression, this obeys force balance. It also means that the compressive stress here depends on the thickness of the glass L, because the thickness of the glass L is appearing in the upper limit of the integral. So if you change the amount of the thickness of the glass, that changes how much area that you have in order to store these tensile stresses to balance the compressive stresses at the surface. And this equation is also telling us that the stress profile here, sigma, is proportional to the concentration profile C with an additional shift. So it's just shifted by this average compressive stress, and then the proportionality constant between the concentration and the stress relates to the Cooper coefficient B, the Young's modulus E, and then 1 minus the Poisson's ratio nu. Now, if we plot this, this shows a plot of the stress as a function of distance going through the thickness of the glass. The x-axis here is just the normalized distance into the glass. So 0 is one side of the pane of glass, 1 is the other side. At both surfaces, we've got our maximum of the negative stress. On this, according to this sign convention, negative stress is a compressive stress. That comes from the minus sign out here. So this negative stress is a compressive stress, and that maximum of the compressive stress is occurring at these two surfaces of the glass. Now, as you go from the outer surface into the interior of the glass, the concentration profile is decaying following the complementary error function shape, and the stress profile is mirroring that with a shift such that the 0 crossing point of the stress here, this 0 stress, is occurring where the integrated compressive stress is equal to the integrated tensile stress. So this 0 crossing point occurs where, if you were to integrate this triangular area here, so this compressive stress on the left, plus all of this integrated compressive stress on the right, those two areas added up have to equal the area of this tensile regime in the interior of the glass. That is what sets the 0 crossing point. And of course, that depends on the thickness of the glass L. The maximum amount of tensile stress that occurs in the middle of the glass is denoted by CT. The CT stands for the central tension. So the central tension is there to balance the compressive stresses. The CS here is the maximum amount of compressive stress which occurs at the surface of the glass. That is denoted CS to indicate compressive stress. And then the distance that corresponds to the 0 crossing point of stress is termed the DOL, or the depth of layer. also sometimes known as the DOC, or depth of compression. They both mean the same thing. That corresponds to the distance into the glass where the stress is zero. So this is where it crosses over from compressive regime to a tensile regime. So there are these three key parameters that we care about for chemically strengthened glass: the magnitude of the compressive stress, the magnitude of this depth of layer, and the central tension. And if you think about this compressive stress as like being armor that you put onto the glass to help protect the glass against damage, the compressive stress CS is like the strength of the armor. The depth of layer DOL is like the thickness of the armor. And then all of that needs to be balanced by central tension here, the CT. One might think that you'd want the compressive stress to be as high as possible and the depth of layer to be as high as possible. However, that increases the integrated amount of compressive stress. All of that has to be balanced by even more tensile stress. And so the trade-off is that, yes, if you have higher compressive stress, higher depth of layer, it's more difficult for the glass to break. However, that requires a very large amount of tensile stresses. So if it does break, it could break in an explosive fashion as those tensile stresses get released. So there is, a safety concern that is associated with having too much tensile stress stored in the glass. Because if you're talking on the phone, if you've got your cell phone up to your face and it breaks, you want it to break in a controlled fashion, not in an explosive fashion. You're shooting small shards of glass into your face. So it's important to make sure that the central tension is kept low enough to avoid this type of what's called frangibility. Now, the applied tensile stress, yes. So in order to break the glass now, basically you're safe until the crack penetrates through the compressive layer and into the tensile layer. So if this is the surface of the glass here, the surface has a whole bunch of little flaws on it. And as long as those flaws stay in the compressive region, you're safe, because the flaws want to open up the glass. They want to create a fracture and tear the glass apart. The compressive stress wants to pull everything together. So the compressive stress is providing protection against the glass fracturing. And you're safe as long as those cracks stay within this compressive region. If the crack becomes long enough that it penetrates through this depth of layer and into the tensile regime, that's where it fractures. Because in the tensile regime, the forces here want to rip the structure apart. It's in tension. That means it wants the glass to expand. It wants to break bonds. And if the crack penetrates into the tensile regime, then that's when it breaks, and it can break in a catastrophic fashion at that point. So as long as the cracks stay in the compressive regime, you're good. If they penetrate through the depth of layer into the tensile regime, that's where it's going to break. Now, this shows some measured concentration profiles in an ion exchanged glass. These were measured by EPMA, electron probe microanalysis. And you can see here the individual dots are the concentration profiles of, for most of these curves, it's the concentration profile of potassium that's measured from the surface of the glass and then going into the interior. In each case, these concentration profiles follow a complementary area function shape. So the individual dots are the measurements from microprobe data, and then the continuous lines here are the fits from the complementary error function, so the EarthC fits. And what you can see is that as time increases, we go from here, this dark blue is a half an hour of ion exchange, shown here in the legend. Then as you go to pink, it's 1 hour, 2 hours, 4 hours, and so on. So here, this is a half an hour of ion exchange. So we go to 1 hour, 2 hours, 4 hours, 8 hours, 16 hours, 32 hours, that you've got more and more penetration of the potassium ions deeper and deeper into the glass. So this is providing a deeper depth of layer that corresponds to that deeper penetration of the potassium ions. The other line here, this shows the sodium concentration that is measured. This is for the half an hour case, and then in this lighter blue for the 32-hour case. And so if you add the molar concentrations of sodium and potassium, then you'd get the total concentration of alkalis, which is maintained as a constant into the thickness, satisfying the zero net flux condition. Now, the next question becomes, what is governing the kinetics of the ion exchange process? And the key parameter there is the depth of layer, or how deep does this compressive stress profile go? And the left-hand plot here shows the logarithm of the diffusion coefficient of the ion exchange process. So this is the logarithm of the interdiffusion coefficient as a function of inverse temperature for 3 different ion exchange temperatures. So this is 3 different salt bath temperatures, 370 degrees Celsius, 410 degrees Celsius, and 450 degrees Celsius. And this is for 3 different glass compositions. This is work that I've done in the development of Gorilla Glass 2, and these were 3 different candidate glasses. And what you can see, interestingly, is that all of these lines are parallel to each other. And what this means is that with this Arrhenius plot here, with this line, which is the logarithm of the diffusion coefficient versus inverse temperature, the slope is what gives us the activation barrier for the interdiffusion process. And that slope is a constant with respect to composition. What's changing is just the y-intercept on this plot. And in fact, if instead of just having 3 different glasses, if we have a whole bunch of different glasses and plot the activation barrier for the interdiffusion process for all of these different glasses, what you see is that they are all a constant within error bars of each other. So each point here is a different glass composition. The error bars are the experimental error bars on the determination of the activation barrier. And this is plotted versus the activation barrier for viscous flow of these same glasses at their respective glass transition temperatures. And what you can see is that although the activation barrier for viscous flow is changing by a lot, it's completely unrelated to the activation barrier for the diffusion process. So what this is telling us is that the Stokes-Einstein relation that we introduced at the beginning of this lecture completely breaks down for this case. So the Stokes-Einstein relation says that the diffusion coefficient is governed by viscosity, which means that there should be a direct relationship here between the activation barrier for viscous flow and interdiffusion coefficient. Instead, there's no relationship whatsoever. So it's a complete breakdown of the Stokes-Einstein relation. And this is because the ion exchange process is, it consists of alkali ions hopping within this glassy matrix. So the viscosity of the glass is governed by how the network of the atoms that make up the backbone of the glass structure, how that network is flowing in a cooperative fashion. But the ion exchange process is individual alkali ions hopping within that network. And so these are 2 decoupled processes as being shown here. So this is giving us some important physical insights. It's also telling us that, that the key parameter here that we can vary is not the activation barrier. It's always about 1.1 electron volts. But instead, the key parameter is basically how much that this line can shift vertically. So it is the intercept here, the D0 parameter, which is governed not by the activation barrier, but by the entropic contribution. So basically, not the activation barrier that the ion exchange process takes place through, but how many pathways there are for the ions to diffuse, to undergo that interdiffusion process. Now, the other key parameter that we need to consider is the compressive stress. So how much stress is being generated at the surface of the glass. And if we plot the compressive stress for a whole bunch of these glass compositions as a function of, say, the glass transition temperature, you can see that, maybe there is some correlation here between compressive stress and glass transition temperature. However, this is a rather noisy correlation if there is one, because if you take a vertical slice through here or a horizontal slice, it covers quite a bit of ground. And so, there may be a relationship, but if we do some mathematical manipulation on this to express this not in terms of stress, but in terms of strain, so using our network dilation description in terms of strain instead of stress. So the strain here is equal to the stress times 1 minus Poisson's ratio over the Young's modulus. Then this strain here causes all of these points to collapse onto a single master curve. So this is still plotted versus glass transition temperature, but plotted in a strain description, causes everything to collapse onto this master curve. And what this means then is that the network dilation here is really governed by the glass transition temperature. And so knowing how the glass transition temperature varies as a function of composition, we can use that information to predict the network dilation and then back out the compressive stress from there. So the overall improvements that we see are quite significant. This shows Weibull plots that have the failure probability versus the applied stress. And this shows just an untreated standard soda-lime silicate glass versus a Gorilla Glass that is chemically strengthened. The numbers on the x-axis have been kindly removed by lawyers, but you can see that this is shifted to a much higher strength. Not only that, but it is a much steeper curve, which means a higher Weibull modulus. And that means that there's less scatter in the strength data. So not only is it stronger on average, but it's also more consistent in its strength with Gorilla Glass compared to soda-lime silicate. So there's a big advantage when it comes to using the ion exchange process to generate chemically strengthened glasses. And that's why chemically strengthened glasses are used on all of your smartphones. Now, ion exchange is useful not just for strengthening glasses, but also to change the refractive index of glasses. And one of the early uses of ion exchange was actually to make ion exchanged waveguides or planar waveguides by basically taking your glass sample and then putting coatings on it where you could then etch away part of the coating and have that etched away part exposed to an ion exchange process where silver ions get exchanged for sodium into the glass. And with the silver to sodium ion exchange process, silver actually imparts a higher refractive index compared to sodium. And so where the silver penetrates into the glass, that localized region has a higher refractive index here compared to the refractive index of the sodium-containing glass where the silver ion exchange has not occurred. And so if you have regions that are locally higher in refractive index, that can lead to total internal reflection of an optical signal. So the optical signal can travel along these channels of higher refractive index where the silver has been ion exchanged into the glass. Another use for ion exchange in glasses is to make anti-microbial glasses. Again, this relies upon silver ion exchange. Silver not only changes the refractive index of the glass, it's also a well-known antimicrobial agent with antiviral, antibacterial, antifungal efficacy. And the way this works is that silver is ion exchanged into the surface of the glass. And then if the surface of the glass is exposed to a humid environment through just water vapor in the atmosphere, some of these silver ions will diffuse to the surface. And if there is some sort of microbe on the surface of the glass, the silver ion is toxic to the microbe, so it can diffuse out of the glass and into the germ, thereby killing the germ. And where this is really helpful is in reducing the spread of secondary infections. So if you've got, say, touch screens that are communal, like, for example, touch screens that are used on ATMs where a lot of people are touching it, that this is able to kill the germs that people may leave on those touch screens. Or if you are in a hospital and have maybe an iPad or some sort of tablet that is being used, you want to make sure that you can help prevent the spread of secondary infections within hospitals. And one way to do that is to have these antimicrobial surfaces that can kill viruses and bacteria on contact. And these equations here, these are just some simple rate equations that were published by my former colleague here, Nick Borelli, in this paper, where you've got the change of the concentration of silver ions shown here, and then the change of the concentration of B stands for bugs. So the basically all the germs here are represented. And so if you've got more potassium, or sorry, more silver ions diffusing to the surface, those silver ions can kill the bugs on the surface. And so you've got these two coupled rate equations that govern this process with the parameters shown here. And this is very effective. Usually these silver ion exchange glasses will last a couple of years or so, maintaining a high efficacy of killing microbes on the surface. After a while, of course, the surface becomes depleted from silver ions and then would need to be replaced. And that simple model that I showed in the previous slide actually has a really good predictive capability to predict the log of a measured experimental kill rate, where you can see this kinetic model here as the solid line and the experimentally measured kill data as the points. So to summarize this lecture, the Stokes-Einstein relation combines Stokes' law with the Einstein relation to consider a relationship between the diffusivity of a particle and the shear viscosity of some sort of fluid medium in which that particle exists. This can be used to describe diffusion in the liquid state, which would be, lower viscosity states. It can be used to describe diffusivity of short chain polymers. However, it breaks down in the case of longer chain polymers, especially where those chains are interconnected with each other, or if there's cross-linking between chains. It also breaks down if you are if you cool a liquid down towards the glassy state. For example, we saw with ion exchange glasses that there's a complete breakdown of that Stokes-Einstein relation. Diffusion of polymers can occur as isolated chains following the Stokes-Einstein relation, or for entangled systems, it occurs via reptation, which is the snake-like motion where the polymer chains are diffusing along their own pathways. And then we covered ion exchange of glasses. We were using, solution from chapter 4 of the book to get the concentration profile of the larger potassium species going into the glass. This is useful for getting chemically strengthened glasses. If you ion exchange in silver, you can increase the refractive index to get glass waveguides or antimicrobial glasses. And in fact, if you diffuse in both silver and potassium, you can get chemically strengthened antimicrobial glasses. And that is commercialized as antimicrobial Gorilla Glass products. So that does it for this lecture. Next up will be the kinetics of phase separation. So thank you very much for listening, and I will see you next time.